So I think this part of desalination process is regarded very often as a less important part of the complete desalination process. But as you have seen on some of the presentation before, post-treatment and remineralization of water is also not only key for health, it's also key for agriculture to have the right mineral composition to avoid these SAR effects, as a sodium absorption rate, deficiency problems. And so that's part of my paper I'm presenting here. Quickly going to the outline of the presentation. We will discuss the importance of the water quality. I think it's good to know, to understand this when we start with the topic of remineralization, that everybody is on a kind of a same level of understanding why do we need post-treatment technologies. Then a little bit looking into cost of that as well. I mean, cost is a big issue always in desalination. What are we doing today? And then what is new in this area of post-treatment? So basically, when we start here, we have some water quality targets. In these targets, we have, let's say, influencing constituents and driving chemicals and mineral factors, which you can see here on that list, like alkalinity, calcium, magnesium, pH, TDS, total dissolved solids, and other special minerals which are part of our daily life and which we basically take out everything if we use desalination processes. So why do we then need all of them? Because we need to create a final water quality with different qualities of, it needs to be stable, buffered, it needs to be protect the asset, which is in some countries one of the biggest issue. They build desalination plants, but they don't do really the good thing to protect the infrastructure. And then, of course, one of our key concerns is that the health aspect of desalinated and remineralized water is not really getting the right attention. And then taste is another thing. I mean, everybody of you, he drinks bottled water, whereas we are desalination specialists, so we believe that people should drink water out of the tap. That's our belief as well. So then turbidity as a other factor of controlling final water quality. So a little bit going back to the needs of remineralization. In the United States, they have identified that because of not correctly treating the water distributed in the pipeline, they will have about 500 billion investments recognized to be spent in the next 25 years just to rehabilitate or to replace infrastructure based on corrosion. Then because of this, you have release of toxic ion like heavy metals and then these typical red water incidents where this can lead to also, if not enough available, to health issues like dental problems, and it also reduces important minerals. So then one of the basic factors to be controlled in the water to have a buffered capacity, which is more related alkalinity to corrosion control properties of the water. So we need to balance the water so that it's stable and it doesn't fluctuate during the distribution within the pipeline. So what we do here then, by adding alkalinity and calcium into it, we try to create layers of different types on the surface of these pipelines. So like calcium carbonate will precipitate, so that's why we typically tend or should have a slightly positive large layer saturation index, LSI. So these are the typical precipitants which are required to have a protective layer. So you could also add some phosphate products to it to create an additional protection to your corrosion issues you may have. But naturally, you can achieve everything by having a correctly balanced water and stabilized water. So as you maybe have read, at least in the United States, this was a big issue even with the presidential campaign in the United States. They were using this case of Flint in Michigan, which is exactly one of the cases where the local water authority didn't took the right care about their water system. So they changed the water source and suddenly they had a big red water incident coming with a high lead level and people who get poisoned by lead. This was also because of not correct understanding of balanced water quality. So then increasing alkalinity, reducing red water complaints, that's what I just said before. And then we also want to have enough minerals in the water, because then most of this water goes back into our sewage treatment plants, and they also operate better if we have more minerals in them, the right balance of the minerals. So then, specifically important are minerals, calcium and magnesium. Here first, calcium. We want to have a calcium carbonic equilibrium, which is measured by LSI, which is more a qualitative measure. And then we can use the now more growing method of calcium carbonate precipitation potential, which is more like a combination of quality and quantitative measurement. So, but more importantly, calcium is required for health purposes. So, as I just said before, drinking water is a very important source of minerals. And I think this is one of the key aspects why we desalinate water and we bring water to the people to drink it. So it should have the properties as we believe when we open the tap, the water comes out in a healthy and good quality. Then, furthermore, what is even less viewed in this market is the magnesium part of that. To add magnesium to it, it's probably regarded as you are here, mainly engineers here. If I bring this up, you say, oh, no. Now somebody have to add something more again. It makes it more complicated. But in fact, magnesium is even more important than calcium. So it linked inherently to many different health issues. And magnesium has a much bigger importance in your body than any other mineral, more than calcium. Especially heart disease is a big problem if it's not available in the water. And around the world, all the desalinated water doesn't contain enough magnesium, as you easily can understand, because we only add calcium or we have calcium sources. So there's an inherently correlated link between cardiovascular disease and people drinking water only from desalinated water, which is maybe correctly balanced but not containing magnesium. So actually there is just, in Israel, they found out some independent study that the death rate in areas where people drink water from desalinated water but not containing enough minerals, calcium and especially magnesium, this has led to an increased heart rate issues, cardiovascular diseases. This is actually ongoing and it's a big topic back on the table in Israel in the desalination space. And some people in the past already, like Kotruvo in the WHO guideline, mentioned that even adding a little magnesium calcium more than we think for stabilization to control corrosion would have a big impact on the health aspect for people. So desalination costs are also one big topic I mentioned before. Basically, post-treatment is the smallest part of in desalination processes. Unfortunately, because of that, it's also regarded as not so important to watch into it, and technologies on the market are, I think, 40, if not years older. You use lime, you use calcium carbonate in simple old technologies. We improve in all membrane aspects, but we didn't look into other methods to improve the water quality at the end. And one of our friends here and original speaker here, Emilio Gabrielli, he mentioned in one of his earlier presentations, and he also presented a paper on remineralization. We spend so much money in development and building desal plants for hundreds of millions, but if you only put very, very little amount of money into the post-treatment to have it rightly made, we would create a much more healthy part for the desalinated water. This is maybe a very specific view on what remineralization can cause if you not completely do it right. So this is a presentation held from a Dutch guy, Rayaert, et al. In 2011, looking on the consequences of not correctly remineralizing water. So there's an economic consequence which is not regarded anywhere in the cost balance in the desalination process and the consumption. As you can see here, this is water which is not remineralized. That means the consequential cost in the economy, especially for cardiovascular diseases and dental carriers like dental problems, is so huge that it adds on top of the typical cost above the zero line. That's the typical cost of desalination processes. And there is an additional cost coming on the back, which nobody sees. It's like cardiovascular diseases, health issues, and dental issues. The same study was made using adding just magnesium in the right proportion to it. It dramatically reduces consequences on cost, on the economy in countries where you have a lot of desalinated water. I don't want to go too long into it. Probably you know all of this. This is current processes, lime dosing on the left side and on the right side calcite contactors. This is technologies very well known to you. If you look on calcium carbonate, this is a simple thing. As smaller the course and finer the calcium carbonate gets, as faster you have the dissolution. There is maybe a limitation. But looking on current calcite contactor processes, it's simple. As smaller as the particle size goes, as faster is the dissolution rate. Of course, there is a technical issue. If it becomes too small, then you cannot keep it in a reactor. You may have DP pressure issues. You cannot operate it in the same method as a typical calcite contactor. So this slide just gives you an indication and shows you that there is an inherent link between the size of the particle, calcium carbonate, and the dissolution rate, or the empty bed contact time in calcite contactors. This shows the difference between coarse grade products, like what you're used in calcite contactors, in millimeter sizes, and then the blue curve shows if you use a micronized product, that's a very fine 2 micron, maybe up 5 to 6 micron product. So we can see there is an extremely fast dissolution rate at the beginning, and it becomes very stable at the end after only 2 minutes. So typically you have an empty bed contact time of, let's say, 20 minutes. You can reach that with micronized calcium carbonate in 1/10 of the time. So actually, there is a new process developed which is quite similar from the setup, but has some very key specific developments which are totally new to this market. So as I said before, the curve was showing micronized calcium carbonate. So we add calcium carbonate in a slurry makedown system, coming from a bypass. There is a slurry makedown with calcium carbonate, which feeds into a so-called membrane calcite reactor. In this membrane calcite reactor, we have...
Jochen, 2 minutes left.
Okay, I will go faster. So we create a calcium bicarbonate solution, and in this calcium bicarbonate solution, which is passing through a membrane, going out, this is a pure high water stream. We add very high reactive milk of lime to it to finally adjust the pH. So no sodium hydroxide, because we don't see a benefit of using sodium hydroxide. So this is a highly reactive milk of lime. This has a very high quality of itself. So it's about almost pure. So we add it to it. It dissolves in seconds without any turbidity left. It's compliant NSF60. It has high reactivity, no residual turbidity. I will go past that. So we also used in the same membrane calcite reactor process dolomite products to add magnesium to it, and we could achieve a very good dissolution rate as well with magnesium. Here is also now a cost calculation where you can see capex and opex cost, and of course as bigger as the plant gets and as a bigger bypass stream we take, we reduce the opex cost, and of course capex will more or less continually slightly increase. A little case study here, just to go through that, is using calcite contactor. You have a lot of equipment and capex cost, like with pumps. You need to pump that through these calcite contactors. Then at the end, you go to a degasser. After degas, you need to pump it again to a storage facility. In case of membrane calcite reactor, that's the same process. We can just need 3 calcite reactor because of the fast dissolution rate. We just need 3 calcite reactor, and the capex costs are dramatically lower. And we don't need pump system. We can go by gravity to this system. There's only a small transfer pumps which are running at much lower energy requirement. You can see this is the same space design for a calcite contactor. Going into our design with the membrane calcite reactor, we are about about 1/4 of the size for the same plant. Cost. Also an issue. The red marked figures you can see, we assume a calcite contactor of a 40 MLD plant costs about 5.5 million. Our process 3.2 million with all the advantages I have explained before. So actually we are doing some pilot trials and now demonstration trials around the world, and we believe this is the future of post-treatment, and our company believes there's more to it than just using lime and calcium carbonate as a coarse product, which we also sell into the market since many years. So that's the end of my presentation.
Thank you.